Hi, so this is question 57. This question has to do with calculating chi-squared using the Hardy-Weinberg equilibrium. So this is a whole equation to use. The issue with this question is that typically in a question that's asking about chi-squared and Hardy-Weinberg, typically when you're finding if something is in Hardy-Weinberg equilibrium, I always say to find your q from the q squared. So typically I would say, okay, we have 10 blue, we know those are q squared, start there. However, we know this is incomplete dominance, so because it's incomplete dominance, we know that it's really not going to follow the Hardy-Weinberg. So the best way to find the number, basically we want to find our p and q, so the best way to find the p and q and the frequency of the alleles is to actually use these whole numbers. So if we're going to do it this way, then basically this is how we're going to do it. So we have 100 individuals. I'm just going to show you here. So we have 100 individuals, which means we have 200 alleles total. If we account for that and we have all of the numbers of the observed, which we do, then we can use these numbers here to actually just figure out what our p and q is. So the first thing we start with would be our p, which is going to be 150 because I'm kind of skipping a little bit, but we see that there's 75 that are homozygous dominant. If there's 75 homozygous dominant organisms that show homozygous dominant, and there's 2 alleles for each, you do 75 times 2, that's 150. Then we have some that are heterozygous. If they're heterozygous, we can just add it straight to 15. We know there's only 15 that would be dominant. So we're going to do 150, the 75 times 2 plus 15, and that gets us 165 out of 200 total alleles, which gets us 0.825. So that is our p, that's our frequency of our dominant allele, because we're accounting for where all of those p's are in the population. Then we have our q, which is going to be our recessive, and where are the recessive found in the population? Well, we know those are 10 because we see 10 organisms that show, again, back to the 10, we see there's 10 organisms that show that they're blue, recessive. So we're going to do 10 times 2, that gets us 20, definitely alleles in the population. The other place those Q alleles are still in those heterozygous. So we can add up the 15 heterozygous alleles. We count for all of the heterozygous alleles in the Q, in the recessive. So we have 20 plus 15, that gets us 35 out of 200 total alleles, so we should get 0.175 for our Q. So the reason we're doing it this way and not just starting off with our recessive like I taught you to do, this is because we know that this situation is not in Hardy-Weinberg because of the incomplete dominance. So we end up with our P, we end up with our Q. Once you end up with those values, then you can figure out the amount that you would expect based on P and Q, the amount that you'd expect to be there. So now we can actually do P squared, which would just take the points, basically the 0.825, and we are just going to, square that. 0.68, that's our frequency of our P squared. 2PQ is going to come out to be 0.28 based on 2 times 0.175 times 0.825, and then Q squared is going to be our 0.175 squared, which gets us 0.03. Once we find out the frequency of these, we really want to put this into a whole number. We want to know how many individuals are actually in each of these. So then we take each of these times 100. We're going to end up with 68 individuals we expect to be dominant, 28 individuals we expect to be heterozygous, 3 individuals expected to be Q squared recessive. Those are our expected. Now once you have those as expected, you're going to be able to plug this in fine. So now you just plug it right in to your chi-square. And if we plug it in with these are expected, and then 75 is what we observed, 15, 10, that's what we observed. If you calculate that all out, you should end up with about 23 I got 23.02, they're saying 23.1, but that roughly is about what you end up with. But again, the reason to do this one differently with Hardy-Weinberg is because starting off, we know this is not in Hardy-Weinberg equilibrium. So if we know it's in Hardy-Weinberg equilibrium, it's really easy to go to the recessive amount. You take the square root of that. You find that it's yet your Q squared. This situation is a little bit trickier. I will say this question took me, I'm going to say a significant amount of time. I mean, it takes probably, I would say at least I spent 10 minutes trying to at least draw it all out and make sure I was correct. So this is a type of question where I would definitely save this one till the end anyway when you're taking the exam, because if you spend this much time on just this equation, I don't know if it's worth that point. So maybe save it till you're done with your other questions, or just, for now, put it on the back. But another good way to interpret it would be, if you're looking at it and you, before even calculating chi-squared, you can see you're going to get some pretty different numbers. They observed 75, you got 68. For 15 purple, really there should be 28, and for the blue 10, we're expecting 3. So we can already, already should be able to predict, even if you just get those, that it's going to be a pretty high number. So it's definitely, hopefully you at least saw that it'd be a high number there. So that's why the correct answer would be D, 23.1. So hopefully that helps you. I just wanted to make sure I explained it and got you all the information. So let me know if you have any other questions about that. All right, thank you.